We already discussed the concept of compound interest, which is interest being paid on interest. Here, I'll dig a little bit deeper and discuss the actual compounding period itself. That is, how much time must pass before interest is calculated and paid and then added to the principal balance. Here's a familiar picture. It shows the growth of $1,000 at 10% compounded annually. So we'd say this illustration uses an annual compounding period. That simply means that after 1 year, interest is calculated, and then that interest is added to the principal balance, and then after the next year, interest is calculated again based on the new principal balance, which includes the interest from the first year, and so on and so on and so on. But what would happen if interest were compounded within a year, say every 6 months? We'd see the growth actually start within the first year. That is, the red part of this figure, which indicates the interest that's being paid on interest, would actually start showing up here within the first year. And as a result, the money would grow at a slightly steeper trajectory. And so we'd see a little bit higher slope here, and ultimately we would get a slightly higher future value. Here's an example with a 6% annual interest rate with compounding every 6 months. So before proceeding, we need to just identify the compounding period. Here it is, every 6 months. And so how many compounding periods are there per year? There are 2 periods per year. Next, we need to take the annual interest rate and turn it into a periodic interest rate. And so the periodic interest rate is just the annual rate divided by the number of periods per year. So 3%. Now that we've done this, we can actually do some math. So let's go to a timeline. The subtle difference here is that I've now got a periodic timeline with 2 periods where each one of these periods is 1/2 of a year. And so literally, period 2, or time 2, is the end of year 1, since there are 2 periods per year. Okay, so the question is, how much interest does $1 earn in a year? And so this is implicitly a future value problem, so I'm just going to say the future value at time 2 is equal to the $1 times 1 plus an appropriate interest rate raised to the second power. Now the R here, once again, needs to be a periodic interest rate, and so I'm going to use the 3%. So the future value is the $1 times 1.03 raised to the second power, and that is 1.0609. And so the answer to the question of how much interest does $1 earn in a year is 6.09 cents. If this were an annual compounding problem, that $1 would only earn 6 cents. Okay, now a quick note on terminology. So we have the annual rate as the interest rate that's stated in annualized terms. It may also be called a nominal rate. And so that's always been our starting point. And so in the previous example, the annual rate was 6%. The periodic rate is equal to an annual rate divided by some number that we're going to call M, and M is just the number of compounding periods per year. Here's a second example. It looks a lot like the first one, except the difference is we now have a monthly compounding period. And so in this case, the number M is equal to 12. That is, there's 12 periods per year. And so our periodic rate, periodic R, is equal to the annual rate of 6% divided by M of 12. And so that's 0.5% per month. Now, when we're thinking about how much interest a dollar earns in a year in this case, and we compare it to the previous example, we should immediately expect a little bit higher number. The reason for that is in the previous example, interest compounded every 6 months. In this example, interest is compounding every month. And so interest begins to be earned on interest more quickly in this case than before. And so if we were going to go through the full timeline, again, keep in mind that timeline needs to be periodic, and so each tick on the timeline is going to represent 1 month. And so we've still got a year represented by the timeline since there are 12 periods. And so the future value at time 12 is the dollar times 1 plus the periodic rate of interest of 0.5% raised to the 12th power, since we have 12 compounding periods. And that answer is $1.06.168. And so how much interest does a dollar earn in a year? 6.168 cents. This chart shows a range of compounding periods from annual to daily, where there's 365 compounding periods a year, and holding the annualized rate constant, we can see that as we go from a low number of compounding periods to a high number of compounding periods, the periodic rate, which is just the annual rate divided by M, of course, declines, and then the interest earned on $1 per year goes from 6 cents up to 6.183 cents. We have a number called the effective annual rate of interest, or the EAR, that allows us to compare compounding periods for the same annualized rate. And the EAR is defined as, for a given periodic rate, the rate under annual compounding that would earn the same interest in a year. So just to build a quick little formula, so let's just think about what $1 would turn into in a year under an annual rate R with period M. And so using the same logic as our earlier examples, that number would just be this, right? So we would take the $1 and multiply it by 1 plus a periodic rate and then raise it to the nth power. So the effective annual rate is just the interest rate that under annual compounding would earn the same amount of interest per year. And so this expression here must equal 1 plus the EAR. And so if you want to solve for the EAR, then you're just going to take 1 plus the periodic rate raised to the nth power and subtract 1. And so based on the construction of this final column here, we actually have the EARs here already. So for annual compounding and an annualized rate of 6%, the EAR, of course, is exactly 6%. From this other end, again, for daily compounding, but for a 6% annualized rate, the EAR is something meaningfully higher. One last note on the compounding periods. What happens if M goes to infinity? That is, interest in the current instant begins earning interest the very next instant in time. We call the M equals infinity case continuous compounding. And one can show mathematically that if m goes to infinity, EAR is equal to the number e raised to the r power minus 1. So there's the continuous compounding case. And going to this example, we say there are infinite periods per year, or continuous compounding. Interest earned in the year is 6.184%, so it's slightly higher than the daily compounding case. Now let's quickly circle back to time value of money problems. And so when we have periodic rates, there's a simple rule that we always need to follow, and that is construct timelines based on periodic rates, periodic ticks, and periodic cash flows. All of those things need to match, and then once you've done that, you can do the math accordingly. So in other words, if we have annual compounding, our timelines need to have annual ticks and an annual interest rate in the calculations. If, for example, we have monthly compounding, our timelines need to have monthly ticks, monthly cash flows, and monthly interest rates in the calculations. To illustrate this, let's go back to the annuity version of the graduation party example we worked in a couple of videos, and we'll modify it for periodic payments and interest. So here's the way the problem was originally stated. You've got $10,000 per year in each of the next 8 years. And when we took that to the timeline, we constructed the timeline as follows, and then we did our calculations, and using the formula, we said the present value is equal to the annuity payment times the annuity factor, and the factor used a discount rate of 5%. That's the annual rate, and its number of periods was 8, which corresponded to the number of years, and the answer was $64,632.13. Okay, if we were to change that problem to a semi-annual party, so we take the $10,000 and split into two $5,000 payments each year, still have 8 years, so we're going to have 16 periods, and still got an annualized rate of 5%. We want to make that a 2.5% periodic rate. How would our timeline and math look? Well, timeline first. Remember, we need periodic cash flows, tick marks, and interest rates. So we've got 16 semi-annual periods on the timeline. We've got $5,000 for each of the cash flows. And then to calculate the present value, we're going to take the new payment and run 2.5% as the periodic rate through the annuity factor instead. And our exponent down here is a 16 instead of an 8 because we've got 16 semi-annual periods. Now this is a different answer, right? It's close, but it's different, and it's a little bit higher. And the reason for that is these cash flows start occurring sooner.